that moves. And assume that in this day or over few seconds, the temperature doesn't change with time. So along this line, the temperature will remain 10 Celsius for 1 hour or so. Okay? The weather doesn't change rapidly. And the same here, 20, same here, 40. They will remain for 1 hour or so. And I want to see how much the temperature of this particle changes with time as it travels. Does it change or no? The temperature of this particle as it travels, does it change with time or no? It does change, right? Because it moves from colder place to a hotter place. How fast does it change? So this is the question. So what is how much dt by dt? How much? How fast, right? This is how fast the temperature change. This is what I want to get, right? How fast the temperature change? Well, first of all, it depends on how fast it travels, right? If it travels fast, it will change fast. So this is, it has to do with u for sure, okay? That's okay, but also it has to do with the direction of u with respect to the direction of the temperature change. Because, for example, if I'm traveling with 100 kilometers per second, but I'm traveling along this curve, will the temperature change? No, okay? So it has to do with the direction of u and the direction of the temperature change. Okay, can you tell me about the direction of the temperature change? If you have any scalar field, any scalar quantity, temperature, pressure, density, whatever, any scalar quantity f, what's the direction of its change? The gradient, exactly. So the gradient by definition is perpendicular to these lines. Okay? So this is the gradient of t. At this point will be perpendicular and so on so. Okay? So this is the gradient of t. So if it's completely perpendicular to the gradient, no change. If it's perfectly aligned with the gradient, this is the maximum change, right? So it has to do with the component of the velocity and the gradient, correct? Yeah, so this is what we call the convective derivative. And if you have both, if you have variation with time and variation with space, you simply add them together to get the total derivative. The local and the convective, okay? Any question about that? Any question? So, for this term, d by dt for the acceleration, this is the momentum equation now, is that rho du by dt is partial u partial t plus u dot nabla u, okay? So this is the total acceleration. Local acceleration and convective acceleration. This is equal to negative nabla p plus mu nabla squared u. And you can see this term, the convective acceleration. This term is what? This term is nonlinear, right? And it's a cursed term, in the sense that this is the source of turbulence. This is the one that prevents analytical solution. This is the one that prevents even the mere existence and uniqueness of a solution and makes it as hard as a 1 million prize problem. Okay? If you can prove that Navier-Stokes equations has a unique solution, you got a $1 million problem. You get a $1 million prize. And it's hard to do that only because of this term. Like I said, it's the source of turbulence that prevents finding of an analytical solution, prevents existence and uniqueness of Navier-Stokes. It's very problematic. Okay. Okay, if it's very problematic, just let's do some scaling. Let's see here the different terms. Which term is more relevant to our applications and which is not. So let's do some scaling of Navier-Stokes equations, which I'm sure you did before, but let's do it quickly. So we'll introduce some characteristic or reference length, reference speed. So the reference length may be the chord of our airfoil. Reference speed may be our U infinity. So as such, the reference time, T here is time, okay, will be combined from these. So L over U infinity. The reference pressure will be, I mean, it's totally free to come up with this. But if we're talking about high speed flows, then it's very convenient to take the reference pressure as the dynamic pressure. Okay? So then we're going to do the scaling. In the sense we're going to define new length. So our old length will be L times x tilde. X tilde is non-dimensional. The same for speed. U is U infinity times U tilde. The same for anything. The same for time is T times T tilde. The same for pressure will be P times P tilde. The same for nabla. Remember, nabla is d by dx, so we're dividing by length. So this is 1 over length. Nabla tilde and so on and so on. Okay. You consider this equation, and let's do another version of it. So we have rho here outside, partial U, partial T. So I will have U tilde and T tilde, and the U will give me U infinity, the T tilde will give me T. Okay? If you have any questions, just stop me, please. Plus, the same here, U tilde dotted with nabla tilde, U tilde. The two U's will give me U squared, and the one nabla will give me 1 over L. This is equal, the right hand side is negative. Again, this is nabla tilde, P tilde. The P tilde will give me P, and the nabla will give me 1 over L. Plus mu nabla tilde squared, U tilde. Again, the U will give me U infinity, the nabla square will give me L squared down. Any question about the scaling? And now we have this T. Remember we said this is L divided by U infinity. So we have here U squared over L. And I have also U squared over L here. They have to be the same because I'm adding. Actually, also this P is rho U infinity squared. So again, I have rho U infinity squared over L like this term. So I can divide everything by rho U infinity squared over L. So you get d U tilde by dt tilde. I'm adding these two terms equal negative nabla tilde P tilde plus. When you divide everything by rho, so I have rho down by U squared, so I have U here because I had U before, and by multiplying by L, so I have L down and still have my mu here. Nabla squared U tilde. So this is your scaled equation. Everything is non-dimensional quantity, and you can see easily as you have done before, here is 1 over the Reynolds number. Okay? And you can see pretty easy here that the Reynolds number indeed, this term was what? How we created the Reynolds number here? Well, we divided the coefficient of the viscous forces by the coefficient of the mass times acceleration. Remember, the mass times acceleration is what? So this equation, the momentum equation, mass times acceleration equal forces. We have pressure forces and viscous forces. The mass times acceleration, sometimes we call it inertia forces, right? So when you do 241, you know that, yes, sometimes we actually move this term in the right-hand side and call it inertia force, and then the equation looks like summation all forces equals 0. They are in dynamic equilibrium. This is what we do sometimes in 241. So this is inertia force, okay? So the Reynolds number indeed is just the coefficient of the inertia force divided by the coefficient of the viscous force. So this is what we know about the Reynolds number. Okay? So Navier-Stokes equation, so it's a very hard equation because of this damn nonlinear term. So what we can do, sometimes we can do exact solution of very simple problem. Like what? Like the Poisson flow, you have here stagnant ball and you have this plate moving with a velocity v.